So I promised in the previous class that we will take that basic script that we wrote and we will start adding an error control code into it. So starting with this lecture, we are going to see a couple of simple error control codes. I'll describe that in the next few minutes. We will first describe the error control code sort of informally, give a very high level introduction on how these things work, and then we will introduce these codes into the script that we wrote for BPSK simulation, see how the whole thing works with the error control code in place as opposed to the uncoded situation, and we'll compare and proceed, etc. Okay. So we'll start with one of the simplest codes. It's the n=3 repetition code. It's a very simple code. The description is out there for you to see. We will start with 1-bit message. Okay, so the message is 1 bit long. So the message could be 0 or 1, right? Right. So message is just 0 or 1. My encoder is going to be a rate 1/3 encoder, 1/3. So it means for every 1 bit that comes into the encoder, I am going to put out 3 bits of the code word. This is the code word. This, like I said, is the message. Okay, and it's 3 bits long. So how am I going to do the encoding? This is how the encoder works. If the message is 0, the code word is 000. If the message is 1, the code word is 111. So you can see why it's called the repetition code and why it's called the n=3 repetition code. Every bit that comes in is repeated 3 times. If it is 0, you repeat 000. If it's 1, you repeat 111. Okay. So after that, like I said, once you have the encoder in place, what you do after that is similar to what you did before. Okay. So if you remember the bit to symbol mapper, the BPSK bit to symbol mapper that we are using has this very simple rule. It takes 0 to +1 and then 1 to -1. Okay. So that's what happens here. So this 0 becomes +1 here, this 0 becomes +1 here, and this 0 becomes +1 there. Okay. So likewise for 1 also. Okay. 1 goes to -1. Okay. So this the symbol vector here takes it's a vector of length 3. This vector could be +1 +1 +1 or -1 -1 -1. And then of course you have noise. Okay, so like I said, it's normal with mean 0 and variance sigma squared. So it's a Gaussian distributed random variable. Mean is 0 and variance is sigma squared, and you have your received vector as s plus n. Okay, so this is the received vector, and that's what you get. Okay, so there will be 3 received values here: R1, R2, R3. Okay, so because of the noise, this R1, R2, R3 could be any value. Okay, it could be 1.1 minus -0.8 minus 1.1, like we saw before. So you will have all sorts of values here. Now the decoder's task is to look at R1, R2, R3 and come up with an estimated code word, estimated or decoded version of the code word. I am going to put code word in brackets, okay, in quotes. I am sorry, I am going to put code word in quotes. The reason is some decoders don't necessarily put out a code word. Okay, so it's just an estimate. We do hope it's a code word, but sometimes it might be slightly better to put out something which is not even a code word sometimes, right? So sometimes that happens. So once you have a code word or a close enough estimate of it, you can go back to the message. I'll comment on that a little bit later, but this is how the overall operation works. Okay, a few comments on the parameters that we had. Okay, so first is EB over N0. Okay, so if you remember, EB over N0 is 1/2R sigma squared. Okay, and R is 1/3. Okay, so if you put R equals 1/3, you will get 3/2 sigma squared. Okay, so this is EB over N0. Okay, remember this is for the rate 1/3 repetition code, right? N=3 repetition code. What happens if you have the uncoded situation? Okay, so if you look at EB over N0 uncoded, the rate is actually 1. So, you have just 1 by 2 sigma squared. Okay. So, notice what happens here excuse me. For the same value of EB over N naught, in the uncoded case you will get 1 sigma. Okay. For the same value of EB over N naught, in the coded case you will get another value of sigma. Okay. So, this is something important to note. Okay. When you do coding for the same EB over N naught, the value of sigma changes, and if you look carefully, this is 3 by 2 sigma square. So, if EB over N naught is the same in these two, the sigma here has to be larger. Okay. So, in the sigma in the coded case, so I will call this sigma coded, and this I will call sigma uncoded. Okay. So, for fixed, for the same EB over N naught, okay, sigma coded will be greater than sigma uncoded. Okay. So, this is something that one needs to remember when you do simulations for error control codes. So, you will fix your EB over N naught and you will find the sigma corresponding to that. Okay. So, now for the same EB over N naught, in the coded case you will get a worse noise, as in sigma will be larger. Remember, sigma is the standard deviation of the noise. If it goes higher, it means you are facing a higher level of noise, the level of noise will be higher. Okay. So, now since we are measuring the performance bit error rate versus EB over N naught, your code has two different things to do here. First, it has to anyway overcome the noise, and not only that, that noise becomes higher in value or higher in standard deviation because of the loss in rate. Okay. So, this is something important, and you can design codes which overcome that also. Okay. So, something to remember. But anyway, let us come back to the repetition code. Hopefully, this is clear to you how this is working. So, the encoder is presumably easy to implement. We will maybe see some implementations later on, and the channel is easy to simulate. Now, what do you do at the decoder? Okay. So, you have 3 values R1, R2, R3. What do you do at the decoder? How do you come up with a code word? Okay. So, there are various strategies, and this code is simple enough, and I can describe from a high level one such strategy. Okay. So, the first decoder we will consider is what is called a hard decision decoder. It is written here, hard decision decoder. Okay. So, we have real values here. Okay. What we do in a hard decision decoder is we directly do not use the real values. We first quantize them or make a hard decision to decide the bit corresponding to each received value. Now, this is not very optimal. You can think about why it is not optimal, because we are giving up a lot of information from the received value and only taking one bit of information. But nevertheless, this is one easy way to think of how the decoder works, and it is quite intuitive. So, one can use a hard decision decoder. So, in many coding situations, people will want to use a hard decision decoder. Maybe the real values are coming too fast, and maybe so many bits of information you can't handle in your decoder, you do not want to. So, for that reason you can make hard decision choice also, but it is definitely suboptimal to a significant level. Okay. So, how do we do hard decisions? Remember, our symbol vector is +1 and -1, and we have this thresholding at 0 as a sort of a reminder. Okay. So, if your Ri is positive, it lies on this side, you want to say the bit is 0. Okay. And if your Ri is negative, you want to say Bi is 1. Okay. So, this is my received hard decision values. Okay. So, now you do a hard decision decoder here. Okay. So, I wrote decoder here, so maybe it is not a good idea to call this a decoder. You make hard decisions here. So, this is threshold at 0. Okay. And then you run a hard decision decoder. So, now because this B is just bits, B1, B2, B3, it is easy to list out what these bits should be. Okay. Remember, even though at the transmitter end the code word was only 000, because of the noise and because errors can happen, this bit vector B can be any one of the 8 possibilities. Okay, what are the 8 possibilities? 0, 0, 0, 0, 0, 1, so on till 1, 1, 1. So, you have 8 different possibilities, and I have arranged them in a nice way here. And if you look at the first 4 possibilities, okay, these are closer to 0, 0, 0 than 1, 1, 1. Okay. So, if you look at 0, 0, 0, if 0, 0, 0 was transmitted, this could be received without any flip on the channel. But you know, if even if 1, 1, 1 was transmitted, you can actually receive 0, 0, 0. But then what should happen? The noise should be so high 3 consecutive times, and you should be able to flip every 0 to 1. Okay, so that may not happen with very high probability. So, you can say this is closer to 0, 0, 0. So, you decide 0, 0, 0. Okay, so you see all these guys are mapped onto 0, 0, 0. On the other hand here, this is sort of closer to 1, 1, 1. Okay, so that is this notion of closeness is in a certain distance. We will look at that a little bit later, but for now you can see intuitively how you do this. Okay. So, this is a version of the hard decision decoder, which is actually sometimes used in practice in many channels where you cannot use real values at the decoder, but it is definitely suboptimal. You are giving up a lot of information. Okay. So, hopefully this decoder was clear to you. It is very simple. You look at the received hard decision value, and if it is closer to 0, 0, 0, as in if it is 0, 0, 0, 0, 0, 1, 0, 1, 0 or 1, 0, 0, you decide 0, 0, 0, otherwise you decide 1, 1, 1. Okay. So, it is one can implement this if needed in MATLAB. Okay. So, one can do an analysis of BER versus EB over N naught. Okay. So, I have shown that here you can see EB over N naught for the coded case is 3 by 2 sigma squared, and probability of error in BI. Okay. So, BI is the hard decision value. Okay. We saw before is Q of 1 by sigma. Okay. So, now 1 by sigma you can rewrite in terms of EB over N naught, and you get this formula, right. So, you put 1 by sigma equals square root of 2 EB over N naught by 3, which is what I have done here, okay, and you get Q of this. So, this is the formula. This is the probability of error in BI. Okay. Now, what is the probability of error in C cap? This is 2 or more BI should be in error. Okay. So, if you put that in, you will get this calculation. Okay. So, this is the case where 2 BI in error, this is the case where 3 BI in error, okay, p power 3, they are all independent. So, it works out like this. So, this is the probability of error. Okay. So, you can express the probability of error in terms of EB over N naught. Okay. So, you evaluate this expression, and here is the surprising and interesting case, interesting situation here. So, this is the uncoded plot, this is the coded plot. Okay. So, surprise, what is the surprise? Surprise is coded seems to be worse than uncoded. Okay. Uncoded. Okay. So, this is a warning. One needs to be careful when you do decoding. You can't do very heavily suboptimal decoding because you are penalizing on the sigma, right. So, EB over N naught is normalized by rate. So, when you reduce rate, your sigma goes worse, and if you do not do good decoding, you can be even worse. Okay. So, you spend so much energy to do coding and you are worse off in EB over N naught. Okay. Now, I would like to point out one more thing. If you plot this BER versus SNR instead of EB over N naught, remember what is SNR? It is just 1 by sigma squared. The R does not play a role. Okay. If you do just SNR, you will see a gain. Okay. So, that is why SNR is sometimes misleading. It is better to look at EB over N naught to be very fair. Okay. So, this is a sort of a negative thing. I was promising a huge shift to the left, I am shifting to the right, but it turns out repetition code is not that good for coding gain, and in fact one can improve upon this, and the next decoder that we see will improve upon this and at least recover as good a performance as the uncoded case. So, we will see that next. Okay. So, this is decoder 2. Okay. So, this is a soft decision decoder. Okay. So, we will not give up the real values. Okay. And notice this is how the decoder works. Okay. So, you look at the distance between the received vector and +1 +1 +1. Remember the +1 +1 +1 is the symbol vector for the code word 0 0 0. So, likewise this 1 1 minus 1 minus 1 minus 1 is the symbol vector for the code word 1 1 1. Okay. So, you look at the received value and you find its distance from the two symbol vectors. What is the distance from 0 0 0? What is the distance from 1 1 1? Okay. But not in terms of bits, but in terms of real values itself, in terms of the symbol vector plus 1 plus 1 plus 1 minus 1 minus 1 minus 1. Okay. Whichever is closer, remember if it is closer to 1 1 1 or the code word 0 0 0, okay, then you declare C cap is 0 0 0. On the other hand, if it is closer to minus 1 minus 1 minus 1 in this distance, you declare C cap is 1 1 1. Okay. Now, this condition involves an finding the length and squaring and all that, but given the structure of this, you can simplify it. So, remember what is this on the left hand side? This is R1 minus 1 whole squared plus R2 minus 1 whole squared plus R3 minus 1 whole squared is less than R1 plus 1 whole squared plus R2 plus 1 whole squared plus R3 plus 1 whole squared. Okay, now you can let me write this a little bit more cleanly. Okay. So, now you can expand this out, there will be a lot of cancellation and this will simply reduce to R1 plus R2 plus R3 greater than minus R1 minus R2 minus R3. Okay. And that is the same as this dot product. You take a correlation with 1 1 1 or minus 1 minus 1 minus 1, whichever is greater now is the closer code word, and in fact that also simplifies to R1 plus R2 plus R3 greater than 0. Okay. So, the soft decision decoder for the repetition code is quite easy to implement. You have R1, R2, R3, you simply check for R1 plus R2 plus R3, okay, and if it is greater than 0, you let C cap to be 0 0 0. If it is less than 0, you let C cap be 1 1 1. Okay. So, it is a relatively easy decoder to implement. Okay. Now, this turns out is an optimal decoder. Okay. You are not giving up anything in this decoding. Okay. It is an optimal decoder, it is called by various names, maximum likelihood decoding, etc. So, this is optimal for probability of block error, okay, assuming uniformly distributed code words. Okay. So, this is the optimal decoder. So, you can't do better than this in decoding. Okay. So, remember the hard decision decoder I mentioned, it is suboptimal, you are giving up a lot of information. This one does not give up any information, it uses all the information in the best possible way. Okay. So, you can't do better than this decoder. Okay. So, it turns out one can analyze this decoder also. I am going to skip the analysis, maybe I will talk about it in another lecture just to give you a brief idea of how the analysis works. But if you do that, this is the picture. Okay. So, remember this is uncoded, this curve is uncoded, this is hard decision decoder and it was worse, and in fact the soft decision decoder lies on top of the uncoded curve. Okay. So, these are all soft decision decoder, the ML decoder, maximum likelihood, or the optimal decoder, and that ends up lying on top of the uncoded curve. Okay. Remember this plot is with EB over N0 in dB, and that is very important. So, the rate normalization that you did, the soft decision decoder simply just about recovers whatever loss you had in this. Okay. So, one can easily conclude repetition code is not good enough for coding gain. So, you will not get coding gain in EB over N0 with repetition code. Okay. But there are other codes which are good. I will point out one more code immediately, and so this also brings out a few important points. So, I will summarize a few things before I go on to the other code. First thing is the code tells you how to map messages to code words. You should implement the encoder, it is easy enough to do, but once you do that, you map the bits one by one into symbols and transmit. You have a received vector, that will be a real valued vector, and that you have to decode to get your estimated code word. Okay. Now, you can do the decoding in multiple ways. If you do suboptimal things, there is a danger of doing even worse than the uncoded case, at least in simple situations that happens. But if you do the optimal decoder, things work. Okay. I have not mentioned too much about complexity. We will see soon enough how these decoders are going to be in practice if you want to implement them. But one important point is you have to design your code well. Okay, if you want coding gain, you have to design your code well, and you have to have a good decoder also. Okay, good decoders are important, codes are also important. So that's sort of a couple of simple takeaways from this whole picture. And what I'm going to do next is show you a small alteration of the script that we wrote before to implement repetition code, how to go about implementing it, and then maybe we'll try and recreate some of the points in this curve and see if we are getting it or not. Okay, so we're going to do that next.